working on a design competition for underwater remotely operated vehicles. I'll let them explain, introduce themselves, and explain the details of the competition.
Okay, so that's exactly what we did. We did a year-long course, not really a course, year-long trial to create a marine ROV, like help to start the marine ROV competition. And we're based off the MATE program, which is the Marine Advanced Technology Education Program. And then next slide. I'm Jesse Smith. I'm one of the engineers, and I'm a junior.
All right, I'm Victor Soa. I'm also an engineer and a junior.
I'm Carson Brown. I was doing the programming, and I'm a junior.
And I'm Will Kepler. I kind of work to bridge the gap between the programmer and the engineers by working, kind of focusing in the electronics.
All right. Okay. So the goals of the project. So there are competitions every year in the MATE program, and we decided to do it over 2 years and compete next year in the 2018 competition. And so the end goal of this entire project is to create an underwater robot that's remotely operated that can perform certain tasks. But this year we want to complete a prototype that could work underwater and move around, but not do those certain tasks, which we'll get to later. So yes. Criteria and restraints. So the MATE competition, it's based on like setting up like your own company or business that's getting tasked with making this product for like use in like the field. And so the criteria of like making the robot is to manipulate objects underwater, take measurements like depth and like mapping and stuff, and it's supposed to collect samples like seashells, and it must have like an array of sensors and lasers in order to do this, like an arm in order to grab stuff, and it must run on 12 volts of power, which is one of the hardest parts to get. And so the MATE competition has several different classes of types of robots that go in water. We chose to do the Ranger class because it was most interesting to us. It did the most stuff. It had the most like complex like underwater like programming. And so other classes include the Scout, Explorer, Navigator, which are like more simpler designs. Like the Scout would just maybe just do mapping or just like images of underwater like landscape. And so we decided Ranger class was the best for us.
Okay, so we did a 2-year program, so we're gonna compete in the 2018 competition, not the 2017 competition, and they're over the summer. And so our timeline for September through January was to build a frame, begin work on the controller and make sure it works, begin work on the motors, get those working, begin work on the ballast tanks, and get the controller connected to the motors. And we've got all of those done so far, and then January-June schedule, we wanted to attach motors to the frame, which we did. We wanted to finish the ballast tanks. We wanted to attach the ballast tanks to the frame, which we have not done yet. We want to connect pumps and valve systems to the tanks for the ballast tanks, and since we don't have the ballast tanks on the frame yet, can't quite do that. And we tested the frame in the water, it was working, and we tested the motors in the water, and you'll see we have a short little video of that, but we have not tested the tanks. Okay, so this is making the frame. We use PVC and ABS. The ABS is the black, the ROV itself. And we use PVC piping and ABS end caps for the main frame part, and this is the control module tank. And images. Here is us working on the frame in Will's house. All of our stuff spread across the kitchen table. Here's like attaching the control module inside the actual frame, preparing to test it, and here's creating ballast using just gravel, which we can get the ballast tanks working yet. And so this is to test it in the water for the final thing.
So I'll talk a little bit about the motors that we designed. There's a video, Mr. Sim, if you want to click on that. So this is just a short little clip of, it's hard to get it going because we had to kind of press the contacts to the motor. So here's, you can see our propeller working underwater with the motor just really quickly. So we designed it same as the rocketry team with the help of Mr. Ested in a program called Autodesk Inventor. So it's a 3D modeling program that we were able to design this and then 3D print it in the printers here at Redwood. And here's a kind of image of it. You can see them each on the motors right here. So I think you need to click to the next one to talk over the video. So kind of the brain of our robot, or as Jesse mentioned, the control module inside of the watertight capsule, it's in a Arduino Mega, which is a type of microcontroller. So if any of you don't know, a microcontroller is a small computer, as you can see, it can fit in this tube, that basically takes inputs that go in through these plugs, and through whatever programming you give it, will then put outputs through the pin as well. And an important aspect that we added to these basic computers was what's called a shield, so it gets placed on top and basically works with the microcontroller so that we can put a USB drive into it, or a USB module that is actually compatible with a Xbox controller, so we can actually control our ROV wirelessly with an Xbox controller. So at the beginning of our grand idea, we decided we wanted to build H bridges on each motor. So what an H bridge is it takes advantage of a very basic circuit, but it can switch a motor to go both directions. So we can push full thrust forward and full thrust in reverse. But as we quickly learned, it was very difficult to wire each individual H bridge, as it requires 4 transistors for each, and just a lot of little tedious wiring. So moral of the story, it was too difficult to execute, and we spent probably hours troubleshooting it. So we ended up just having to totally simplify it. Here's a drawing of our circuit on a basic level. So we have our voltage coming in through the motor, and then it runs through, this is a transistor, which is basically an electronically actuated switch. So we can give our Arduino an input with the controller, and it will then turn on this switch and allow current to flow through the transistor and back out. So it's just an on-off, very simple, no H bridges system running our motors. So I think Carson will talk more about the controller.
So basically, for using the controller, we started with a USB to wireless adapter that we plugged into the shield that we'll mention, and we use that to connect the Xbox controller to our brain. So that allows us for the use of lots of buttons on here, which we wanted to have lots of functions pre-programmed, so we can have it auto surface, auto go down to a certain depth, stuff like that, auto grab stuff. And we wanted to make it use joysticks, because that would make it really easy to control underwater and use kind of finer controls, as opposed to just having a switch that turned on and off the motors. So we just used the Xbox controller in conjunction with the wireless adapter to USB, and then that plugged right into the Arduino. And so for our code, we had to adapt through kind of several steps to make everything work. So the controller went into the Arduino, and then in the Arduino, we determined the joystick positions with the axis, the value of the axis, and then we used all that data on both joysticks to determine what the user is telling the ROV to do. And then, based on that information, we use the PDA groupings of variables. So, for example, to go forward, we pair these two, and then we turn both those on at the same time so that the ROV goes forward. And then using those temporary variables, we set everything to false, because we don't want things to turn off that we don't want, or things to turn on that we don't want to turn on. And then we assign all those temporary variables to the correct value based on the joysticks. And you can see here kind of like a controls all these transistors, which then controls the motors. And using all those variables, we turn on and off the motors based on them. So, for example, if I press forward on the controller, it turns on 2 variables, and then those variables go to the motors, and then everything works. Right, assuming everything works. Yeah.
So, a little bit of testing and troubleshooting, as you can see, here's kind of our initial wiring. It's kind of a rat's nest, as we needed to make it really small and compact so we could fit it in this watertight shell. So our dry run was a success. We were able to use the controller to turn on and off motors, as Carson was saying, with the Xbox controller wirelessly. And then we kind of wired everything through our control module, and things started to go weird. Motors started to turn on when we didn't want them on and stay on, and then didn't turn on. It was all very weird and very frustrating. And then altogether, some of the motors stopped responding. So we kind of had to go through a troubleshooting process of looking at individual transistors and how they were behaving. We found that when we touched them, they were like burning hot. So I kind of was scratching my head, and we were going through transistors, and I ended up calling my mentor for this project, Zachary Lendenberg, who pointed me towards the data sheets of the components, which I probably should have looked at before. So we were using TIP 120 transistors, which are Darlington transistors. So they're usually used as an amplifier in a circuit instead of a switch like in a transistor radio. So they have basically their schematic inside the tiny little package is 2 transistors. So as you bring voltage in here, it'll turn on this switch and this switch, and this is much better for boosting your current. But as Zach said, MOSFETs will change your life. They're metal oxide semiconductor field effect transistors, and they are basically meant for power transmission. So they're a much simpler schematic down here. So basically the gate gets a low voltage from the Arduino, which is how it turns it on, and allows current to flow through very simply. So instead of having down here, and actually if it's too hard to see, I'm trying to put a lot on here, in each of your information sheets you can see the graph in it. It shows that at our nominal current of 2 amps, which is the max that competition will allow you to draw, we have a voltage drop across the transistor of, I believe, here, let me pull it up, I can't read it, of 1.8 or 0.8 volts. So when you work that out with the math, you get 0.8 times 2 amps, which comes out to be 1.6 watts power dissipated across that transistor. So our transistor, our TP120, had a max dissipation of 2 watts. So if you wanted to run it at that nominal point, it would burn up. So we were just burning up these transistors basically and frying them. So what we need to do is get a MOSFET, which doesn't behave like this. It only, so it has a separate kind of set of behaviors in that instead of changing its voltage that's dropped across it as the current increases, it just has a constant resistance across it, so it behaves like a resistor. So basically you just have to get a MOSFET with the lowest possible resistance. So we went online and looked through data sheets, and I finally found a resistor that would allow us, or a transistor that would allow us to run our 2 amps through it and be totally fine. So we now have these MOSFET transistors. Got them here with me today, and we are currently in the process of rewiring and switching out each transistor in our rat's nest down there.
Yeah. Alright, so these are images that I took of Will trying to do some robot surgery. So we were getting ready to test it in the water when things started getting wonky, and we had put all of the electronics inside of the housing, and by the time it was starting to go wonky, and we were like, oh shoot, should we take it out? And then we decided not to because we didn't want to rip anything, and so Will had to like cram his like hands in there and figure out what was going on, and that's how we found out that the transistors were burning up because he was like touching them, and so we have not yet taken anything out because we didn't want to rip anything yet as we start to replace the transistors. But yeah, so it does look quite messy, but it did work for a little bit. Alright, so our goal after 1 year was to get a working prototype in the water, and we did not reach that. We got it to work for a little bit on dry land, and but when we started putting things together, it started to not quite work as we planned. But it did set us up well for next year and to continue our 2-year-long process in getting the competition completed with. And that is all. Thank you.
Any questions?
Yes.
You guys said the Ranger one was more interesting. Like, what made it better than the other categories?
Well, one includes an arm in the design, so that's part of our next year's goal. We're gonna incorporate an arm into the design, and it does more complex like tasks. Like the Scout was more just about like mapping and like taking images, and the Ranger's like you have to like move stuff underwater to like different locations, as well as map, as well as get the depth, as well as like bring stuff back to the surface. And so we thought it would be more interesting to do that. Yes.
Build versus buy question. You can buy H bridges that are the size of my thumbnail, commercial off-the-shelf part. But were you prohibited from doing that, or you just wanted to give yourself the challenge of implementing it yourself?
So the issue with something that small is like a lot of it is like we were looking at some of the bigger like breakout boards that are H bridges that could handle the amount of current in stuff we were pulling, because these are pretty sizable motors like underwater with propellers, and just like financially we were kind of trying to like build a fairly inexpensive prototype at this point. So we were looking, and the cheapest way to do it was going to be to build our own H bridges, and then we just got to the point where we said, whatever, we already have the components to do this right now, so we just switched it over quickly.
Are you gonna work on it over the summer?
Yeah. Yeah, it was the timeline goes through June as well. We kind of did that, so we haven't met all the check marks yet, but we will continue to work over the summer and through next year as well.
Is it freshwater or saltwater?
They'll be in pools.
It'll be a pool.
But they're supposed to be built for saltwater.
Yeah.
So.
Yeah, the applications are for like underwater like construction and stuff in the future. So it's gonna be in like the oceans. Yeah.
Are you required to do it wirelessly, or can you use a tether if you want?
Well, you're required to use a tether. It's all wrapped up right now. Our controller is wireless, just like to wherever the module is. You're not actually allowed to have any onboard batteries, which is part of the issue because we're using like the microcontroller is actually powered by USB or 9-volt, but we're using a 12-volt system, so we're actually running, in addition to our 12-volt power supply down to power motors, a USB cable down to the Arduino so we can run our controller and power.
The details of the new competition will come out.
Oh yeah. So the 2017 competition had like specific tasks, and the 2018 competition will have different tasks, which is why we decided not to like incorporate certain sensors or like the arm quite yet, because we don't know what it has to do for next year. And so the details for that will come out, I think over the summer.
Yeah. This year they were required to have a depth sensor so they know exactly what depth, so you can measure from A to B, and based on that you get points. And it was like supposed to have a, I'm not sure how you pronounce it, it sounded like a ramen laser or something, some sort of laser on it so you could measure certain samples, and you have to have a camera on it to like see where you're going, but also to read certain things at the bottom of the pool.